5.6, ratio and root test. As we've seen with some sums of the form the sum from 1 to infinity, the series of a sub n, such as the sum or the series of 1 over n and the series 1 over n squared, it's actually not enough that the sequence itself, the sequence that defines our sum, that it goes to 0. It has to go to 0 fast enough. So n squared converges, it's p series, and 1 over n is harmonic, and it diverges. And it's also a p series. But there's a slight difference in the exponent, right? 1 versus 2. So it has to go to 0 fast enough. So the ratio test helps us determine how quickly the ratio of successive terms are coming together, and hence if they are convergent. So first, the theorem, ratio test. Okay, let the series be a series with non-zero terms, and let rho equal the limit as n goes to infinity of this ratio, the absolute value of the ratio, a n plus 1 over a sub n. If rho is in between 0 and 1, could be including 0, then the series converges absolutely. If rho, that ratio, is greater than 1 or infinity, then it diverges. But if rho equals 1, then the test is not conclusive. We don't actually know what happens there. So let's dive into some examples. And I'll note that it is very useful when we have exponentials and factorials because, the ratio simplifies significantly. So we'll see this here. All right, 51. Use the ratio test to determine whether the series converges or diverges. And we have this series 2 to the n over n factorial. So first we want to take rho. So rho equals the limit as n goes to infinity of a n plus 1 over a n. Well, the n plus 1th term here is going to be 2 to the n plus 1 over n plus 1 factorial. And I'm going to go ahead and multiply actually and take the reciprocal of the a sub n term rather than dividing by a fraction. I don't want a complex fraction. This is going to be n factorial divided by 2 to the n. Now, as I said, things simplify very nicely here. All right, so 2n plus 1 and 2 to the n simplifies to 2. And our n plus 1 factorial and the n factorial reduce to n plus 1. Now, I'm dropping the absolute values here because, n is going to infinity, so it's going to be positive. So this entire fraction is positive. And so that limit is 0. Let's go back to our test. If it is 0, then it converges absolutely. Right, so that means by the ratio test, and it's a good idea to always sum things up like this. The sum n equals 1 to infinity of 2 to the n over n factorial converges. And if you recall, converging absolutely means that it converges. Okay, that implies that. So there we are. All right, next, 52. Use the ratio test to, do the same. Determine if this converges or diverges. All right, so rho is equal to the limit as n goes to infinity of, I'm going to skip that first step and just go straight to my n plus 1th term would be n plus 1 to the n plus 1 over n plus 1 factorial. And multiplying by the reciprocal of my a sub n, my nth term, this would be n factorial over n to the n. Okay, well, what can we reduce here? The n plus 1 factorial and the n factorial reduce. I'm going to leave my absolute values for the time being. So I get n plus 1, and then I have an n to the n, and the n plus 1 to the n plus 1. Now, what can we simplify here if we keep that absolute value? Well, it appears we might be able to rewrite this actually as an exponential. That should be equal to as n approaches infinity of... yes, okay. So what will happen here, let's just explain the algebra, is we have n plus 1 in the numerator n plus 1 times. So we can cancel one of those, the n plus 1, to make this just n plus 1 to the n. And then we have the exponent of n we can apply to both of those two things, and this is all going to be positive. So this is going to be n plus 1 over n to the nth power, which, if you recall a little bit of calculus 1, that is equal to 1 plus 1 over n to the n, which is e. Now, e, again going back to this, is greater than 1. It's 2.71828 roughly. So this is greater than 1. Therefore, by the ratio test, that series n equals 1, n to the n over n factorial diverges. I believe we have one last for this. Use the ratio test. No, we have two. To determine if this diverges or converges, of course. All right. So our n plus 1th term is where we need to go next. We still have our limit. We never want to leave off that limit, by the way. If you notice, I've carried it all the way through until we actually apply the limit, so don't drop that. That will be n plus 1th term, negative 1 to the n plus 1. We have an n plus 1 factorial squared. We're definitely going to expand that in a moment. And that'd be 2 n plus 1 factorial. Pay careful attention to what's happening when I do the n plus 1s. I'm changing all of my n's. I'm subbing in n plus 1 for my n's. And then I'm going to take the reciprocal of that. So that will be 2n factorial over negative 1 to the n factorial squared. All right. Let's again just do some algebra here and show what that actually means. So the negative 1 to the n plus 1. Okay, we don't really have to worry about that. These two are going to play nicely. Those two will cancel out, actually. But the n plus 1 factorial squared means we have n plus 1 factorial, n plus 1 factorial in the numerator. Okay, we've got in the denominator an n factorial, n factorial. And as far as the two n's, we've got 2n factorial, so that's all of our even numbers. Factorial down, multiply down to 1. And then we have the 2n plus 2 factorial. So that's one more even number. Notice that. Now I'm going to go ahead and drop the absolute value bars, but the reason I'm going to do that is I'm also going to drop my negative 1 to the n plus 1. Because those two simplify. These two simplify to be a negative 1. The absolute value of negative 1 is positive 1. So it becomes irrelevant. All right, let's see. Bringing this over here. So the n factorial cancels with the n plus 1 factorial to be n plus 1. And we actually have two of those. So n plus 1 squared. That would be these two terms. And these two terms. And then these two, because 2n factorial, okay, that's 2n, and then 2n minus 2, 2n minus 4, 2n minus 6, factoring down, or multiplying down, the 2n plus 2 starts at 2n plus 2 and goes down. So you may need to write out the terms to convince yourself of that, but that will be 2n plus 2. And then we've also got the 2n plus 1. Yes, okay. So it'll start at 2n plus 2 and work its way down by 1s. All right, and if we take our limit, let's see, well, this would actually be, we would have an n squared term in the numerator. Just write this in here. That'd be an n squared up here. And down here we'd have a 4n squared. Okay, it's approximately this. So then our ratio, or our limit here, is going to be 1/4. The ratio of our leading coefficients is 1/4, and so our limit is 1/4. This is less than 1, which means that our series converges. So by the ratio test, that series, -1 to the n factorial squared over 2n factorial n equals 1 to infinity, converges. Our last ratio test question. We're hopefully getting to be old hat at this. So let's just dive in. We have our ratio, and that is going to be n plus 1 cubed over 3 to the n plus 1 multiplied by, again, taking the reciprocal of this for our nth term, 3 to the n, and we have n cubed. Again, all the terms are positive here, so the absolute values are useless. They don't actually serve a real purpose, but they were necessary in example 53, if you notice that. All right, so some things simplify. These two become a 3 in the denominator. 3, and then we have our n plus 1 cubed and an n cubed. And for that same reasoning in the last one, this ratio is, or this limit, because of our ratio, is going to 1/3, which is less than 1, and so by the ratio test, n cubed over 3 to the n converges. Moving on to the root test. The root test is very similar in nature. Our conditions are different, but our conclusions will be the same. If rho is equal to 1, it's inconclusive. If it's greater than 1 or infinity, it diverges. And if rho is greater than or equal to 0 and less than 1, then it converges absolutely. However, we define rho differently. Okay, rho is a limit of the nth root of the absolute value of an. That's why it's called the root test. Okay, so this is very useful whenever you have something with a lot of n exponents. A lot of n exponents. This is related somewhat to logarithmic differentiation, actually. All right, number 55. Use the root test to determine if this converges or diverges. All right, well, by definition, rho is the nth root of the absolute value of a sub n, which in this case is the nth root of n squared plus 3n to the n over 4n squared plus 5 to the n. The nth root eliminates those exponents. I left out something important. I got happy. N goes to infinity. Don't forget those. Let's make sure that's very, very clear. Okay. Nth root of that. And so the exponents are eliminated because of the root. And I should put the absolute value bars here, but it really, again, at this point is not going to make a lot of difference for this particular one. So this would be the limit as n goes to infinity of n squared plus 3n over 4n squared plus 5. Now, same logic as in those previous questions, this limit is 1/4, which is less than 1, which means that by the root test, that series, n equals 1 to infinity, n squared plus 3n to the n over 4n squared plus 5 to the n converges. Example 56, use the root test. Again, if you notice those n exponents, so we can at some point begin skipping a few steps in there. So rho is equal to the limit as n approaches infinity of the nth root of n to the n over natural log n to the n. Exponents reduce. So this is the limit as n of n over natural log n. Now we can apply L'Hopital's rule here to show that this limit works, because both of those actually go to infinity. So this would be the limit as n approaches infinity of 1 over n, which is equal to the limit approaches infinity of n, and that's infinite. Therefore, by the root test, n to the n over natural log n to the n, this one to infinity, diverges. Last example, use the root test for this. We have the series n equals 1 to infinity of 1 over n to the n. So again, let's take rho equal to the limit n goes to infinity of the nth root of 1 over n to the n. Now if you notice, there's not actually an exponent on the numerator. However, I could easily write this, and that now be true. Doesn't change the value, because 1 to any exponent is just 1. So that would mean, and I should note, I'm also dropping the absolute value. I haven't written them for a few of these, because the terms are all positive. Okay. But for completeness, I should probably put those in there. Yeah, okay. Go ahead and put that there. Right, so this would be equal to the limit of 1 over n, which is 0. Now, because that is 0, that means this converges absolutely. By the root test, series n equals 1 to infinity, 1 over n to the n. And again, because converging absolutely means that it converges. There we are. Now, this one actually should make a little bit of sense, because as the exponent gets larger, I mean, it's acting like a p-series, but the exponent is going to infinity. So as long as that's bigger than 1, which it always is, we have that.